Hi, in this chapter we will introduce feature effects. We start explaining the term global feature effects using the linear regression model as a starting example, and then motivate why, especially in machine learning, we are also interested in local feature effects. In the subsequent chapters, we will also introduce specific methods for visualizing global and local feature effects. Let's look at a simple example of a linear regression model without interactions. In this example, we see the feature temperature, which is used to model the number of bike rentals as the target. The linear regression model estimates one single weight that can be used to interpret the marginal effect of temperature with respect to the number of bike rentals. This means that the interpretation applies globally to all observations, no matter which observation we have at hand. If temperature increases by 1 unit, then the expected number of bike rentals will increase by better head units. Of course, this makes a linear model so attractive because you have only one single value to interpret to understand the effect of temperature. However, the drawback is that the model will be limited in its flexibility. We have learned about GAMs. GAMs estimate nonlinear effect of features and are a bit more difficult to interpret. Instead of having now a single value better, as in linear regression, we now have a function which we ideally can visualize. However, we cannot represent the shape of this curve with a single number. While this is possible for linear lines, it's not possible for curves, like in the nonlinear GAM case here. However, GAMs allow to visualize this effect so that we have a curve that describes the global effect of temperature in this example. As we can see, also the data points seem to be fitted better because in high temperature regions, the effect seems to drop, which was not possible in the linear model. To go one step further and motivate the local view of feature effects, let's look at what happens if we include interactions. Including interactions here will modify the marginal effect of the feature temperature and make it dependent on certain observations. For example, in the linear regression, we now have multiple slopes instead of one single value. This means we would have 4 different values to explain the marginal effect. For the GAM case, we have 4 different curves to describe the marginal effect. The term local means here that we have single lines or curves that apply only to a certain number of observations. For example, this line here applies only to observations belonging to the season summer. This makes our linear model more flexible, but we need more coefficients to interpret. As we know in linear model and GAMs, we need to specify these kind of interactions manually. However, machine learning models often learn automatically these nonlinear effects and complex interactions. This means that in machine learning, we would need to look at local feature effect methods to analyze the effect of individual observations. There's still the possibility to analyze global feature effects in machine learning by aggregating local effects to a global curve or a global number. However, this will always lead to information loss, as we will see later. To sum up, feature effects visualize or quantify the marginal effect of a feature with respect to the predicted outcome. They are similar to regression coefficients or splines, as they can interpret the effect of features. Because machine learning models are so powerful and can estimate highly complex interactions and nonlinear effects, we usually should always look at local effects as well. Different aggregation levels for feature effects exist to make the explanations simpler to comprehend. Of course, this is a simplification and we will also have information loss here involved. We will later learn ice curves, which basically visualize the effect of single observations, meaning that we will have one single curve for each observation in our data set, which represents its effect on the prediction. Oftentimes, individual effects can be aggregated into a global effect. The partial dependence plot does this. Essentially, it aggregates all the curves from the left plot into one aggregated curve, which can lead to information loss. Another aggregation level allows to condense the information of the curve into one single number. The so-called average marginal effects estimate the slope at different positions of effect curve and aggregate these slopes at different points to get a bigger picture and understand the average effect across different features, for example. Of course, this would make more sense in settings where we have, for example, only monotonic effect, so that the averaging won't cancel out positive and negative slopes. In the subsequent chapters, we will dive deeper into ice plots, partial dependence plots, and as alternative ale plot, but won't discuss the average marginal effects. We hope that you understood the main differences between local feature effects and global feature effects.